indeed a pleasure to be here, because it switches time for a second about 30 years back, which is always good. Actually more than 30, I'm afraid. And so here was the great experience which I had at Stony Brook when we met with Blaine Lawson and we thought about scalar curvature. And at that time we thought we understood it reasonably well. But then I thought about that. But and so I'm supposed to say something about scalar curvature. This is kind of the subject matter of my talk. And but at least at the beginning I wouldn't say much, partly because I still, the more I thought about that, less I understood what it is. I just don't know what it is. And so it may be somewhat got this kind of a talk. And then I thought how it's related to other very simple kind of elementary things, which I thought were really much easier. And then I realized I don't understand them either. But because they're so simple elementary, I can explain you the questions. Yes, there's absolutely childish questions. On one hand, on the other hand, they're related, and what you can prove about them involves scalar curvature, but themselves they're seemingly not related to that. So I start with the following kind of exercise, which I find very charming. You take a simplex, and this simplex is correct, yeah? Not quite, no? But what's relevant, we have 6 edges, yeah? In this position, you can count them. But the way if you have points like that, you can more or less immediately say, this magical number 7, someone believe people can immediately kind of grasp numbers below 7 the maximum. But in truth, of course, it's 3. Maybe they were genius. People can grasp 3 or not 4. For 4 takes about half a second to grasp 4. If 6, no way you have to count. 10, absolutely beyond any understanding. But in this position, you can see 3 plus 3, it's 6. And then you have another simplex. And there are corresponding kind of faces and edges. And so there are the dihedral angle there between pairs of faces. And this IJ, is from 1 to 4. There are 4 maximum faces, and there is another one with that. And then, if there is this inequality, it implies equality. So there is a little theorem, and I think it's quite a fantastic theorem. And I must say I learned it rather late in my life, and it's corollary of something. Kirchberger theorem. I'm confused about how to pronounce this here. Kirchberger theorem or whatever. And this just exercise for the audience, and it's easy but not trivial. Yeah? And then just look around it, what you can say to make more. This is known, and then immediately doesn't require much imagination to start modifying it and generalizing it. And when you start doing that, so amazingly you run into problems. So one simple for a mathematician, and if you're not a mathematician, maybe somewhat more painful, is to go to high dimensions. And so this is always our kind of attitude. Dimension goes up, right? And then you have simplex of any dimension. You have a simplex of dimension n, say 1, and this will be prime. And also rather the dihedral angles. I prefer even denote them this way now. We see alpha ij, and there are alpha prime ij. And so ij goes in n-dimensional space. So this goes from 1 to n plus 1. And if you have this inequality, it implies equality. That's the theorem. And of course, if you prove dimension 3, you prove it for any dimension. Dimension 2, it's too easy, yeah? Because the sum of angles 180 degrees. And it is not true. There is no such conservation law for higher dimension, but still there is something, yeah? And actually the proof, which I know intuitively, is kind of clear, right? If you have like cones or something, and then there is a plane, and you start turning it, some angles become bigger, but some become smaller. They cannot become simultaneously all bigger or all simultaneously become smaller, right? But actual proof is, I don't know, a geometric proof. Yeah? You write some simple formula, scalar product at a time. Yeah. But we see in Euclidean space, there are not so many kind of interesting general theorems which go to large world of Riemannian manifold, and this has kind of a few remarkable generalization. But concerning usual curvature, but as far as scalar curvature is concerned, let's try to generalize it in two different ways. So how we can generalize it? So one dimension goes up, up, up. Actually, if it goes to infinity, I don't know what happens. If you take an infinite dimension, what exactly happens there, I feel uncomfortable. I don't know if it makes sense or not to ask this question in infinite dimensions. But another way to generalize it, you can say, why simplex? There are other polyhedra. And then if you take cube, for example, this is also true. We have a cubical type polyhedron, but I am not certain actually it's true in exactly this form. If it's just a rectangular cube, something I will say later on about it. But if it's just general shape of a cube and the planes are in general position, if you can deform it, making all angles bigger. Of course, now you can move them. Yeah, you can. It doesn't have to be cube. Yeah, it may be rectangular solid. You can move faces by parallel translates. In the case of simplices, they remains homothetic to the original one. Here they change their shape, but you still cannot, at least for the cube, you cannot make angles smaller. I'm not certain you can make them larger. I think you can. I'm just not certain about that. And the same issue remains for other polyhedra. You may have complicated polyhedra. And you ask a question, if you start moving their faces, when you can make the angle smaller or bigger, and what extremal configuration. When you arrive at sum, you cannot make it either smaller or bigger. And I don't know that. Okay? So many things which I don't know. And this is kind of elementary question. And then you may ask, well, in general, we have a big polyhedron, what kind of angles can be? And also there are many very kind of not obvious points here. For example, one kind of simple observation is what a polyhedra where all angles less or equal pi over 2. So if you hit all the angles like that, then it's not difficult to show the product of simplices and cubes. But if you put here little epsilon, then become not so clear what happens. What a polyhedra, the IP, and there are rather complicated polyhedra, but they will have a rather interesting shape. And this is not, again, but this will be kind of one direction to start thinking. It's not where I want to go. But there is another way. If you come from differential geometry, you can say, well, straight lines, planes, whatever, it's not our kind of life. We want something to be curved. So imagine you now have curved polyhedron, a curved simplex. How you can curve it? Yeah. So again, for the usual, say, triangles, we know, as I said, you cannot deform it enlarging the angles. Now let's allow curved lines, but the curve must be under some control. Imagine you make them convex. And of course, if they make them convex, these angles in this picture becomes bigger, and this is simple formula for curvature. It's easier to prove. However, if you do this for simplex, yeah, now you consider curved linear three-dimensional simplex. Well, all faces are convex. Can you say that it's impossible at the same time all dihedral angles at all points, but now we have curved surfaces meeting around the curve. So all these angles at all points simultaneously become smaller. Of course, when you push them outside, it seems the angle must become, at least somewhere, must become bigger, but can you show it, you can make it smaller. In dimension 2, dimension 3, it's manageable question, and then when dimension goes up, I'm not that certain. It's still rather elementary question of convex geometry, but still I thought when I first look at it, it might be obvious, of course, yeah, but then I just couldn't prove it for higher dimension, even for simplex. And then even more so, the question arises for general polyhedra. So I take a polyhedron, like a cube, or whatever specific polyhedron, and if I can deform it in this space, such that all faces become convex, and simultaneously all the dihedral angles become smaller. And this seems to be absolutely, well, we don't know that. For simplex, I think it's manageable, because we understand it well. It's manageable for cubes, but it's not so clear not so clear in general. And then if you look at somewhat more carefully, you see that actually convexity is not quite right concept. You can make next level of generalization and say, aha, because if you want to look at what will be extremal configuration, and so you take this convex thing and pushing them in, and we push them in, kind of angles become smaller. And so you can push and arrive at extremal configuration, making flat in, angles smaller and smaller, and then you think at a flat object. But when you push and minimize them, what you get, of course, not flat, because this boundary was not flat anymore, but minimal surface. And therefore, the correct condition is that these surfaces have, and here I'm going to say what it means, positive mean curvature. Mean curvature positive. And now this is what I want to explain what it is. This is a technical condition. I'm not going to say what is mean curvature. And I think in this kind of mathematics it's essential. You have this something by itself making no sense. But the sign of this does make sense. So many concepts in curvature of this kind of mathematics. If you say curvature is positive, it doesn't mean there is some curvature, it's some number and it's positive. It means it's just an indivisible property where this term by itself makes no sense possible. And for surfaces, there are two different definitions of positive mean curvature which in general and full generality diverge. And one says the following. So it is, yes, this kind of a picture, positive mean curvature, if you move it outside. So for every move, small move, yeah? And here it's important, every small move. Outside in this direction. So this concept of sign-dependent direction. If you look from one side positive, from another side will be negative. This is, by the way, how it's extremely difficult to remember who is convex, who is concave. Yeah, it depends from where you stay. Yeah, whether this room is convex or concave. Yeah, and so this is, and this will kind of concept of being outside. Every small move increases area. So this is supposed to be surface, yeah, it is not something one-dimensional, so whatever you take little deformation localized here, but it must be small. When you push it outside, it becomes bigger. Not surprising, right? So this is curved, and of course this becomes bigger. And the same is true inside, but now it's different. It says there are small deformations which make it smaller, but this is the wrong deformation. It's inside, but it's maybe bigger. But there is a deformation inside which make it smaller. And so there are two different definitions, and a priori they're different, right? So if you don't say anything about what kind of surface it is, it's probably they're different. I haven't looked at it very carefully, but I think easy to make examples. But if it is smooth, it is the same, and that's a remarkable thing. Why it's the same? Yeah? Completely different. Think two different quantities. Here it says here it means everything. And here it says only existence of certain deformation. When you go in this direction, it becomes small. Of course, the idea is when you push it there, area goes down. In this direction, it goes up. But this is a very different quantization. And this is typical of curvature. Curvature has many faces where, because of linear algebra, can become often identical. A priori, they're different. So we have this mean curvature concept. And then the question which we have is as follows. So I have a polyhedron in the Euclidean space, high dimensional, or much of this is quite significant, meaningful in dimension. In dimension 2, it's convex polyhedron. Actually, it doesn't have to be strictly speaking convex. Well, I would rather safer to have it convex. And then I'm asking if you can deform this polyhedra, become very much curvilinear, so that all faces become kind of positive mean curvature, so looking a little bit outside, and simultaneously all the hedral angles become smaller. So this depends on polyhedron, and when it's possible, when not. And there are classes of polyhedrons when it is impossible, and I don't know any example when it's possible. And so in the basic example, the simplest example for that, which I shall explain the proof a little bit later, is n-dimensional cube in any dimension. There is a cube, and if you have rectangular, which is the same for this purpose, and you cannot deform it into space such that all faces start pushing a little bit outside with positive mean curvature, and simultaneously all angles become smaller. That's impossible. And however, it's not clear, amazingly enough, that if you have equalities indeed, so all faces have zero mean curvature, so the minimal surfaces, no matter where you push them, they kind of become bigger, and all angles exactly pi/2, it must be rectangular solid. That still, for the moment, I think is unproven. And even proof of this, what I said for the cube, the simplest proof, which is, I'm 100% sure, follows from the kind of the measuring gradient will be the Archie-Singer index theorem for Dirac operator, which is somewhat bizarre, yeah? It's such an elementary statement. And then this where scalar curvature enters. But this is somewhat bizarre, I must say. And there is alternative proof, which is, I'm not certain 100%, depends on the recent result by Sean Yao, which I haven't verified, and the proof is by far more complicated, partly because of this. So that's kind of one line of thought. And so the issue is understanding angles, the hydral angles of convex polyhedra, and how they may be modified when we allow this polyhedra become curved linear polyhedra. And of course, these are rather special instances of what you can look upon. So that's class 1 of the problems to which you arrive thinking about scalar curvature, which is not here so far. So it's number 1. So let me summarize it. So the question is, what are possible the hydral angles of polyhedra with phase of positive mean curvature? We say convex, yeah, easier to say convex in general sense basis. So, and so there are kind of simple conjectures, and just which I said, that extremal polyhedra must be, that's usually convex polyhedra, and you cannot deform them, making them faces convex, looking outside, simultaneously making angles smaller inside, which is, again, intuitively extremely transparent. And
so in this context, when you're looking at dihedral angles,
right,
they're not constant necessarily along an intersection, right? Because when you're allowing...
You're absolutely right. I will say dihedral angles, small and big, meaning at every point.
Every point.
However, you can assume they're constant. It doesn't. You can reduce to the case when they're constant. And it is they're much more kind of, you can reduce it to rather canonical pictures. But you don't assume they're constant. No, you assume scalar curvature, this mean curvature constant, but again, it reduces to the case when it's actually zero and angles are constant. Modular singularities which may appear. So this is a question number 1. Now I turn to question number 2. So you may ask something more about the question number 1, if you have some. I'm not 100% surprised. So, it's very easy if somebody can give me a solution immediately. It may be that simple. I don't know. I thought for a while, but who knows? Yeah, there may be obvious way. But even I said, even when faces are convex, not just mean, just even for that case, which looked completely obvious, I couldn't find simple proof. Yeah. So to my surprise, it's no mean curvature is really convex body, and in face are convex. Of course, angles, when you push them back, angles will become smaller. But unfortunately, pushing them in does not kind of work so simple. So now number 2. Will be completely different questions, seemingly nothing to do with that. But geometry, when you start proving something, will be the same as here. So here I want to explain what is another part of the curvature, what is the boundary of the curvature of a surface. So when you have a curve, So what characterizes its curvature is how far you have to go from it to arrive at the two normal lines come together. When you have a circle, and then the center, and then this normal line to it come to one point, and this is, at every point there is this focal radius. You take two nearby points and move them together. And then this line may never, of course, if you go outside, they kind of diverge. But when you go inside, at some moment they come together. And so there is this number r, is focal radius of this point. And the same true for any surface. We have a surface now, and again you can move one normal in nearby another normal line, and they may go forever, never coming together. But if you take something like spherical surface, of course, when you come to the center, any two come together, but the radius means, so we say that radius greater than something. Again, what is radius is kind of, is often, we work with inequalities, and we say that this focal radius of a surface at some point is greater or equal than some number r if you take any two nearby points here, and if you take this any two normal lines, and they never meet either here or here within distance r. So you have to go at least distance r before they meet together. And by the way, this makes sense even for when you have a curve in a space, yeah? You take normal, there may be normal lines which come together, some don't come together, but if no lines, no rays coming near this point which are normal, and they never come together within time r, you say that focal radius at this point is bigger than r. And you don't have to know what it is, just this inequality. And again, it makes sense in a way, for, in a greater generality than I said. As usual, inequality have advantage of being defined when equality is not quite defined. So this is now the issue. What we want to understand is the following. Here, now, I consider unit ball in the Euclidean space. You see, I put this n here because it's not b by times b times b, because this indicates power. And when this is r times that, and when you write b to the n, it's a little bit confusing, right? Because it's not equal, right? b times b, right? This actually I was taught from my professor Rocklin, yeah? Who was saying it's very bad to put this power, that power here. And I just stick to that. Not everybody shares this kind of attitude. Because now in tech, when in tech it's hard to usually position it in the right kind of size, yeah. But still it's better than it was before that. So I'm concerned about unit ball. It's unit ball. And I will be interested in surfaces sitting inside. It's n-dimensional, and so my surfaces will be, my surface y will be n-1 dimensional in this ball. And so what I want to understand, what are the possible, depending on something, properties of the surface, which in a second I shall describe, how big this r can be. So given this y, and then I want to define this focal radius, yeah? I say focal radius of my y greater than r. For certain y. For example, if y is flat, this will, then of course no lines come together, it's okay. If I have a sphere, we say unit sphere, this will be a unit ball, and something will be the unit ball. So the boundary of that, it's n-1 dimensional sphere, then this focal radius, of course, equals to 1. And now my question is, if y is topologically more complicated, and so just look at some examples. So what happens, what kind of...
Or you don't care?
For the moment, I said nothing here. It may be open, may be closed, but I will consider some example which motivates what I'm going to say next. For the sphere, we have that. And now we just look at other kind of standard instances of manifold sitting in a unit ball. And the next example, if we consider spheres of different dimension, say, so k, no, let's start with the 1, yeah? Which actually, so I said it's how many times k times, and this notation will be like that, yeah? And that's the right notation because this is a one-dimensional circle being a torus, you see? When you write for sphere sk, it's somewhat convenient because s is not notation for the circle. And it's not power anyway. Yeah? Or this notation for the sphere, which is good. So it's one-dimensional. It's a circle, and see, I put here 1. So let me it's to use correct notation. Yeah? So I have this torus, and where this torus sits, because usual torus is usually unit circle sitting in the up to, and so this will be sitting in Rn, which is 2k. Right? But how big this radius is there? See, if you see what is the size of this, by the way, yeah? It's not at all inciding in the unit ball, but the size of the ball it sits, this radius of the ball will be, well, up to a constant, maybe 2 times, I keep forgetting, maybe 2 times here, or something like 2 here, but approximately, yeah, up to a constant. It's square root of k. Right? And this is Pythagorean theorem, of course. So when you multiply, naturally, and therefore if you scale it back to the unit size, and so the radius it has will be the same as for the circle, my radius will be 1. But when I scale it back, it sits now in the unit ball, and the radius become like this, yeah? So, and you ask, can you do better? So can you put this product or somebody else inside of the unit ball, which is product of circles or actually product of other manifolds, such that the radius will be bigger? So the natural conjecture would be, let me formulate it. That if I take product of any kind of manifolds, closed manifolds, y1, y2, and yk, and I put it into Euclidean space whichever dimension, then the radius of this guy, as defined, will be less or equal, well, maybe up to a constant, square root of k. Yeah, this is, it's in a unit ball. Yeah, you're absolutely right. You're absolutely right. And this may be actually infinite for all we know. And here again, I must admit my complete helplessness. I cannot prove any kind of estimate here for large n. Yes, no, nothing. I even cannot prove that there is any kind of bound at all. Maybe it's all bounded by 2, by 3 or something. Again, it's unclear to me it's my phenomenal stupidity or it's indeed phenomenally difficult question. Yeah? But I haven't thought too many, I mean, not my life, because I came to this question relatively recently. So that's the question. Because, you see, the fact it is a product which makes difference. So what you can say, what is known? Now I say something you do know, and that what about some other manifolds? So these were embedding in mid-dimensional. You multiply circle and space twice as big. The easiest case consider when you expect such estimates, when you have somebody of dimension n minus 1, and this sitting in the ball of dimension n. So what you can say in there? So one, let me bring forth some example. So what you can say here, and just the usual sphere sit there with radius 1, this we understand. But now look for exotic spheres, and because Milne is here, yeah, you just don't give them the name, yeah. You don't know who invented them, right? You just don't hear it. And so the remarkable thing is that for some of them, so there are certain spheres of dimension 1, 2, and 4 mod 8. If I'm not confusing, I always confuse about that, which if the right numbers. So if this manifold is in this category, again you can show that this radius will be less or equal some constant square root of n. So for certain of them. And for some of them you don't know. Nothing. I mean, you can say nothing at all. But so, it only for this dimension, if I'm not mistaken. Right? 0, of course, I think 0 is also here. It's powers of 2. And if it's some other dimension, nothing is known. Another example, when you know better, in this where torus come in, back. But if this manifold was topologically torus, then my inequality becomes better. It becomes that this radius must be smaller than some constant n. What the hell? Small radiuses. This goes to 0. I apologize. Yeah.
Sorry, presumably the codimension of the embedding is not just one.
Yeah. Okay. It must be immersion. Okay. It's not embedding. It doesn't have to be embedded. We have self-intersection. You're absolutely right. You're absolutely right. That's a good point. Yeah. Otherwise, well, it has to be. You cannot embed it there. And if it was a torus, but now it's again, it can be embedding, it will be 1 over n. Much better. None of them, I think, is optimal. So I guess here you have bigger exponent. Conjecturally, it will be 1 plus epsilon. And for spheres, I have no idea what to expect. So, and again, the only way, so for all incompleteness, so there are 2 definite statements which I made. So this for the exotics, for some exotic spheres, and this for tori. And the only way to prove something which I am aware of is with appeal to the Scalar curvature. And in one case of this exotic spheres, it's again Archer-Zinger index theorem. In the case of a torus, it's a different argument, where index theorem is rather useless. Well, you cannot prove this index theorem. So all I can say, yeah. But again, it's not. And well, the difficulty, of course, you have somehow to use the fact that topology is the way I said. So you have to somehow incorporate in this geometry. You have to incorporate this topology, and they don't look to fit actually very much. Yeah? And there is no visible curvature anywhere. So that's what makes it kind of amusing. And now I may say some words about proofs and about more general statements. So what at the time? So some momentary. So far I tried to be non-technical, and in particular, didn't in this discussion. All you had to know what are Euclidean spaces of high dimension, and what are smooth submanifold there hypersurfaces. And your intuition from dimension 3 works really well. However, the interest of this statement is very much when dimension goes to infinity. I mean, it's not just estimate, but estimate of that kind. So, now let me try to explain what it has to do with scalar curvature. And my issue was all the time what I was thinking about, looking at this question, is to understand what is scalar curvature. Or rather, which I saying many times, what it means this curvature is greater than a given constant, which may be positive or negative. So we want to understand the meaning of this in most possible general terms. And again, my kind of conviction, the more I think about that, the more I'm getting convinced that definitions which we usually accept and use are not correct definitions. They don't cover all the range of possibilities, the range of properties which displayed by scalar curvature. Okay, but till now I'm starting giving incorrect definitions. So I know the incorrect, I don't know about the correct ones, but the ones to which you can prove something. Okay, so my apologies. From this moment on, I have to apologize. I don't know the right definition, but that's usual. I think any mathematical definition, if you think it's right, it's certainly probably not. And then, after some thinking, you realize it's wrong. Well, but you still use it. So, to define scalar curvature, you know what are the object to which it applies. And the object it applies are Riemannian manifolds. So, with Riemannian manifolds, so what they are. And here we have facing exactly the same problem. I think and they were quiet for a while. It was a kind of big discovery, and this definition, I think, was given by Riemann and then kind of developed, and we studied them for a long time, and I think we arrive at a healthy situation. We don't know what they are, right? Because there is something we have to go beyond them in a way. Yeah, certainly they are there, but there is more to them this definition, usual definition suggests. Yet I'm going to give some definition, right? Riemannian manifold. And the way it was, one way to think about them is as follows. So much more elementary concept, which again, now when you start thinking about them systematically, all of them become questionable whether your definition are correct, but it is a concept of a metric space, which came later, but it's much more primitive, is simply a concept than Riemannian manifold. So, and metric space is a set. Again, we assume we know what it is. I mean, it's also not so clear. Yeah? So there are points. No, indeed, yeah, there is now much change in mathematics. And when you apply, especially when you start to apply mathematics outside mathematics, something happens when you apply it to theoretical physics. And another, which I was supposed to give another talk, when you apply it, for example, to biology, to languages, immediately see that basic concepts of mathematics has to be changed. They are not adequate, starting from concept of a set. Right? And for the languages, for instance, if you ask if you can say there is set of sentences, and they'll say no. What does it mean? How you know if sentence is there? Unless you wrote it down, it's not in the language, right? So you write it, and so it changes all the time. So it's not really set, right? It's a different. It means you cannot apply usual operation there. It's not, and it's not. I think it's a joke. I think one of the problems people had in developing artificial intelligence exactly they were taking literally some mathematical concept and trying to apply them, but they're not adequate. They're just temporal. They're not kind of absolute. But still, we stick to them because they're still so good, yeah? Not because I believe they're ultimately right. So there are these points, and there is a distance, concept of a distance between these points, which has some way, is positive, and the key property is triangle inequality. If you go from here to here to here, then there is the shortcut will be shorter. Right? So the distance between these points less than sum of the two, and which, by the way, correspond to certain diagram. It can be reinterpreted in certain terms. But anyway, it is. But the point is, of course, when you say this definition, how the hell you know given function two variables it has this property? How you construct such a function? It's very kind of a priori extremely difficult to have it. It's if you really write it as function of two variables. So function of two variables is kind of a tricky thing. Yeah, it's not so easy to study its properties. Well, you can say all these words, but in practice, you never define distance in this way. Secretly, there is function in one variable, and this is how it was invented by Riemann. And it was so we have to use function in one variable, and this function, in fact, will be not one function but many of them. And so, actually, what you have many functions where it's symmetric function of ij, and it's symmetric in ij. And you can say, aha, you can write that. And again, this we know is wrong. This is kind of so physicists would never do that, and there's a good reason not to do this. Because the moment you order them, you introduce structure which was not there, just symmetric. Okay. So you know that Jij equal Ji, and Ji, and so this is a bunch of functions, and such that this matrix is positive definite. That's another kind of thing which now make me cringe when I say matrix. What the hell is matrix? Yeah? Does anybody has a mathematical definition of a matrix? It is not a mathematical concept. It's something related to the blackboard and what I write. And many things in mathematics are like that, you know. You think they're abstract, logically defined concept, but it's illusion. And again, it's illusion which is prevents us from understanding much in mathematics, in fact. Because matrix is, you know, it's table, mean tables. It's not a mathematical concept. It's unclear. Well, you can make some artificial definition adapted to a particular case. They're not mathematical, and nothing wrong with that. But they're not mathematical. So when there are claims for rigor in mathematics, it's absolutely misplaced. Mathematics is the least rigorous of all natural sciences. It's not natural sciences. Except the only field which is less rigorous than mathematical logic, which is absolutely lack even elementary rigor. No, it's not a joke. And let me give some kind of evidence in this direction. You know, one of the people who was introducing this logic and was extremely kind of careful about that was Frege. And he introduced this rigorous notation and created this mathematical logic. And then, when he was about to publish one of his papers, or books actually, he wrote the books, and he sent some preliminary version to Russell. And, well, Russell immediately found contradiction. Not a mistake, but his action was self-contradictory. And so, Frege was extremely upset because we have an obvious axiom coming from his mind was wrong, but definitely something was wrong. But again, why the hell he trusts coming from to somebody's intuition? No, if you have experiments, you can repeat it billions of times. You can't have trust it. But if you come from intuition of one or two men, you know, this piece of meat under your skull, why trust it? It's absurd. Yeah? Logic depends on intuition, which is absolutely the least trustable thing. And then Russell wrote his text, and then Gödel commented itself. Well, Frege was, of course, disaster, but Russell much worse. It's every mistake on every line. And then you know that he proven his theorem and his famous Gödel theorems. And you know how what is the proof? The proof of his second incompleteness theorem. What is the major step of the proof? Yeah? And he says, well, it's a little bit major to prove. It's kind of obvious that and nobody, I don't think the rigorous proof was ever written. And his first theorem, full of mistakes from a certain point of view. Right? So mathematics is not that rigorous. So and particularly it's good we have metrics. It's not mathematics. We are not rigorous. Yeah? We can't use these words. Yeah? Otherwise we'll die if we try to be rigorous. For example, you know that you cannot use self-referential sentences. But human language, including mathematical, cannot exist. It collapses if you don't use them. You say this theorem, and this is already self-referential. Right? The theorem on the previous page. So you refer to something, to the manuscript, which is not subject to your language. And you refer to this all the time in mathematics. In mathematics would be impossible without that. Or human language, or anything. Yeah? So the basic principle of logic unapplicable to mathematics. So, and of course, logic does this mistake all the time. Yeah? But anyway, this is little diversion. This is what I was about to say in my other lecture. Yeah? So we have this matrix, and what is this matrix is, of course, matrix is a bad word, but what we have in fact is positive, definite, etc., which means at each point we actually have tiny little ellipsoid, right, which corresponding to unit ball in this matrix, namely, I think about this as a quadratic form, forget about this. On one hand, it's a bunch of function. On the other hand, in each point we have this ellipsoid, which says who is unit ball with respect to this kind of Euclidean metric. So all vectors, so if you write this quadratic form, subject 1. So you can think in two terms. I don't want to translate. Either at every point you have an ellipsoid, and there are finitely many parameters for this ellipsoid, or you have this metric. And then granted that, you can define the distance. So how you do that? You imagine this depends on point. Yeah, these are actually functions j of your x, and x is your point in the Euclidean space. And at every point, so you have this ellipsoid. And you say, hi, ellipsoid the same as a ball. Declare this at this point to be unit ball. And you declare this to be unit ball, and then you have a new metric on the Euclidean space. So at every point, thus you introduce new Euclidean metric, slightly different from the original one. And then you say, what is distance between 2 points in this metric? But they take very, very nearby points. And then you go to the next point and do the same. You have another ellipsoid and another distance. You go from point to point, add up these distances, and then make distance smaller, smaller, and smaller, and go to the limit, and then among all these sequences, choose the one which gives you some minimal, right? And then it becomes a function to variables. So, but you started with so many n minus 1 over two functions in one variable. And function in one variable you can describe, you can say what positive definite, which is, by the way, not so easy, by the way. Positive definite is not innocuous condition. It's very, very kind of heavy, but still is better than triangular inequality. And you create in this way, the world of matrices was done by Riemann. You have a question? Plus 1, okay. I trust you. I don't check it. So the point is, given the bunch of functions, so many, in one variable with certain condition, you create a metric on the Euclidean space. And these are Riemannian metric, and then you can, I don't think Riemann was thinking in global terms. For him, it was the end of the story. This is already quite a remarkable thing. You can you do it for the Euclidean space. But then you can say, if you have one such space with such metric, you can take pieces. You don't have the whole space. Take another one, and then these two happens to be isometric, meaning there is a transformation between them, gluing them with map, which is isometry. And then you create much complicated space like sphere, right? Kinds of two balls, each of them can be imagined part of Euclidean space. So defined, you glue them together, and you have spheres or other Riemannian manifold. So you have a concept of Riemannian manifold, which is metric given this way, and then it's only true locally, and then it has more room, doesn't have to be topologically constrained by anything. So that is Riemannian manifold. And now how we can define scalar curvature. It's a curvature, and in the simplest case, we have, say, unit sphere, and it's a curved surface, and the definition which I'm going to give should assign to some number, and in general, so you have Riemannian manifold X, scalar curvature of this X, or which has a metric, is a function of X. So it's supposed to be some function on the manifold depending on this metric, constructed in certain way and having certain properties. So for the sphere, it might be something positive. And of course, for the sphere, for the two-dimensional sphere, it kind of uses as a kind of measure of that, and it's a question of normalization. Of course, you can choose any number, then multiply it by constant. Of course, as usual, normalization is questionable, right? What is the unit sphere? Depends from where you look. What is the unit? Meters, centimeters, yeah? So it can be. It depends what you call, what is the unit of, what you call for unit. But now, what are essential properties of this? So the most essential property of scalar curvature, so my objects are metric spaces where there is a concept of distance. But they come by this kind of Riemannian tricky way. They're in a way very simple. The construction was not that simple, but they kind of are relatively simple. So one principle of any kind of curvature, it kind of goes without saying, if you multiply space by a constant, curvature divided by squared. So what does it mean multiply space by a constant? I have my space, whoop, I multiply distances by a constant, whoop, contract them. And then how curvature is supposed to change. You see, it's different from the curvature in this curve. If you enlarge by some constant the curve, curvature multiplied without the square. But the curvature intrinsically for surfaces is supposed to behave in this way, and this needs some justification. But because this curvature is intimately related to areas, and which I don't have time to explain, but it's because curves intrinsically have no curvature. Being this curved or this straight line, when you live inside, you don't see this curvature, and therefore, but it's only starts visible when you have a sphere, something two-dimensional, and you go in different direction, and you see it's different in different. Flat space and non-flat space become distinguishable intrinsically. it's number 1. But now, specifically, scalar curvature has the property that it is, and it's defined locally. So you don't have to know what is this manifold. It's enough to remember locally it was Euclidean space, and there was this bunch of function j, and just at every point you only look at this function and measure this curvature. All right. So it's locally defined, but then you'll have global effects, which I was mentioning. And so it's a function assigned to that. And the most fundamental property is that if I add two such things, so I have a space of, I have Rn plus Rm. And this was metric here, and this was metric there. And I add them, which means I just take sum of at every point. I take this matrix. Here I write J, and here maybe I put by the write G prime, yeah, after all. They're not so different, yeah? And here will be G prime KL. So if I take this big thing, then the scalar curvature of this adds up. Scalar curvature of scalar curvature of G plus scalar curvature of G prime. That's basic property. And that rather constricts. It actually makes it somewhat reminiscent of entropy, just if you think about it. But I never could realize what is, if there is a direct link between this and entropy. Entropy behaves exactly in the same way. So, but I don't know if there is true similarity here. I will be not surprised if it is some link with entropy. And but this, of course, doesn't define. So almost defines, but not quite. And then there is the last property which I just want to say is as follows. So I have my matrix in the Euclidean space Jj, so I have this ellipsoid. And so I choose a coordinates in my space, and I always can choose coordinates in the space, so my metric will look like Euclidean metric. Say it will be point of 0, right? Imagine my point is 0, yeah? And this was 0. And then nearby it will be like Euclidean metric plus O of x squared. Not big O, yeah? So it's approximately Euclidean at every point. So there is a such coordinate system. So this quadratic form will be sum of squares, right? All the j become, at this point, become 1. So the matrix become like that. 1, 1, 1, 1. And all terms here will decay quadratically when we come close to 0. So let's use this coordinate system. This coordinate system kind of unique. So imagine I take this system. And so what the property which I want is as follows. So I have this bunch of functions on the Euclidean space and choose this coordinate system. And now using this coordinate system, Euclidean, imagine point is 0, just to, I can say it is 0. The orthogonal group acts here on this Euclidean space, and it acts on them on these matrices as a function. You go around and average of the group. And the scalar curvature doesn't change. That's another property of scalar curvature. It's stable under averaging if you rotate around the point. So no matter from where you look at this, it's completely kind of the same, yeah, in suitable coordinates. There is no preferred direction. And this uniquely defines scalar curvature, all these properties, except for normalization. You have normalizer. And so normalization is, so all these properties say it's kind of rather simple creature. And now normalization come, and all you have to say, scalar curvature of the unit sphere equals 2. Not 1. You see, it's 2 rather than 1. Because exactly you don't want to say I greater than j in some formula. You make some summation, and you don't want to say that, which is, and that's little theorem saying that this indeed defines uniquely the scalar curvature. This is defined and unique. It's not difficult, and well, it's close to the right definition, but it's not right. Yeah, you know, it's not, but it's kind of the best I know with the minimal kind of assumptions. And then now, hopefully time is over, so I don't have to say what comes next. Yeah. The remarkable thing that there is non-trivial link between topology and scalar curvature. In Riemannian geometry, there are other kind of theorems between scalar curvature and geometry, but with curvature and geometry, they're kind of accidental. There is no good fitting, very much unlike algebraic geometry, Eulerian geometry, but indeed there is intimate relation between topology and geometry. But in scalar curvature, it is absolutely kind of basic. And just to give an instance of some argument what scalar curvature has to do with what I said before. Let me say just one word, for example, how we can show in a rather artificial way, and it is what I'm saying. I know it's something very artificial, and I hate saying that, but I don't know how to say it better. What I said about the cube, that when you have a cube, you cannot have on such a cube faces being with positive mean curvature in all the hydral angles less than pi/2, right? So what it has to do with scalar curvature. And the point is, if you start we can reflexing this group, this torus in all kind of possible direction, and then this cube covers Euclidean space, and you have the singularities, of course, where one attached to another. However, the metric which you have, it does have a Riemannian metric, which Riemannian metric only continues. It's not smooth because of what I said. However, because of the assumption I made about angles being quasi-acute and this curvature positive, you can approximate this metric by a metric with positive scalar curvature. And this is just one of the dilemmas we had with Blaine a long time ago, because positive mean curvature fits very well this concept of positive scalar curvature. And then we have this invariant metric here, where this is a group operate, and then the quotient of this gives you a torus, and this is the same torus which was appearing before. And so the essential property of this torus is, it's again a theorem which has a variety of authors, which admits no metric of positive scalar curvature. And the reason for that, and there are different ways to look at them, but the easiest one is the fact that, and this is kind of the last fundamental property of scalar curvature, which I cannot discuss, that scalar curvature related in a kind of another remarkable way with Dirac operator. And Dirac operator, in a way, is a kind of a differential square root of the Laplace operator. Whatever it means, which of course I have no time to explain, it's kind of in the same way it's square root of Laplace operator as in dimension 2 the Cauchy-Riemann operator is square root of Dirac operator, right? We know holomorphic function are harmonic, and there is a similar class of equation for any Laplace operator. And then the square of, I'm sorry, and this square root, however, is not truly Laplace operator. It's a kind of a Laplace operator plus multiplication by scalar curvature is my normalization multiplied by 4. And therefore, when scalar curvature is positive, this operator is positive, its index is 0, and then it's confronted with the theorem Ati-Singer saying, aha, under some condition it's non-zero. And this way, you can show torus, for example, might be careful how to do that, has no metric of positive scalar curvature, and in particular my cube cannot have these faces bulging outside and still angles less than pi/2. But this is certainly a horrible proof, right? Because we do use ready up machinery instead of understanding what is the geometry of this cube. You cannot see it inside of the cube. And this is a beginning of this our non-understanding. So there are many questions. We start doing them. We can prove something, but the proofs are all such that they say, we don't understand. We just concoct the proof for this purpose, only to say there is a set of interesting questions, well, interesting maybe, maybe not, which we don't know how to answer, and which involves maybe implicitly rather interesting kind of basic, like index theory, certainly basic mathematics of 20th century and of 21st. Yeah, that's the end of the story. Yeah.
So I guess the point you don't like here is that you have to approximate your given distance function with a...
No, they have to. Why I have to reflect? Why cannot? Why should I reflect? I have to see inside, because this is already special shape. Many shapes, they're not reflection for anybody, and then you have this problem. That's this approximation is bad enough, but it's not the worst. The worst, of course, reflection. But you need special symmetry, special angle pi over 2, because it's one. Because 2 is integer, right? And imagine you have polyhedra where these angles are not kind of fraction of pi. That's what the hell you do. Already for simplex there is, for three-dimensional simplex there is somebody's paper where the person claims he can do it, but I haven't checked it. I'm not certain it's correct. There are a variety of alternative approaches, but well, much of this is unknown. But reflection, so the question you want to understand what it means in terms of Dirac operator inside of the cube. So you need some kind of a reflection condition. And this happens in other occasions when you have differential operator and there is kind of ugly boundary condition, and then you, by some kind of trickery, you regularize and go to another manifold. Maybe it's trickery, maybe it's inevitable. Maybe there is no way to say it inside of this singularity. It must be a quotient. This is not, again, I don't know. There are quite several similar situations in geometry. And to prove geometric inequalities, you have to do something like that. Represent your manifold as orbifold, but possibly with an even continuous group action, but then become regular. And it is rather picture so far unsatisfactory. Maybe you should do it, and maybe nothing wrong, or maybe you're just missing something. I don't know. But again, we only can prove, among the questions I mentioned at the beginning, you can prove them only in very, very special cases, and usually much weaker than what you expect, right? And still you use rather sophisticated kind of mathematics, which makes, in my view, quite kind of tempting to try to understand better.
But do you think, I mean, in particular, in this kind of proof, it's really crucial that you smooth the metric, so you could even talk about the Dirac operator. But if you try to use minimal hypersurfaces,
yes,
maybe you can get by without smoothing. And
you're right. With minimal surface, you can go without smoothing, and then you have some. Because it's still easier to do this way when you smooth. I agree. You can do it with, exactly. You can do it with minimal surface up to the point if you fully trust this how they work here. You certainly you can do it without smoothing, but again, in either of this method tells you that if you have equality, then it will be standard cube. That's neither Dirac operator exactly. This is approximation or singularity called the problem. Again, the smoothing is certainly artifact. I agree, it is a very unpleasant artifact, but it's, for me, it's at this point it's minor, which I can believe everything is true without smoothing. But what to do with reflection group? This is more fundamental obstacle. And this appears at least to other occasions, when it happens and can be somehow bypassed. Sometimes you can, sometimes you cannot. Yeah. So.
Other questions? I'm sure we have plenty of questions we'd like to ask in private. So why don't we thank Misha now and